All right, so in this video, we're going to extend what we have just done to multi-head because that was our fourth version. Our fourth version of the of attention mechanism is the multi-head, and this is the final step, the final part of this chapter. In the next video, we'll probably just do one or two cleanups in maybe one or two videos, but this is the core of it. So this multi-head, it just refers to that we are going to divide this attention mechanism into what we're calling heads. And those will be multiple, as the name says itself. And they are supposed to operate independently. What we did was to look at a single head intention. That's what we looked at right now. Oh, in the previous video. And what we had there is considered a single head attention, where there's only one set of attention weights which process the input sequentially. What we're going to do in this video is to intuitively build on this, to build a multi-head attention module. And then we will, in the next video, we will discuss how to make it better, just like we have always been doing. So we are going to build on top of our causal attention. There's not much theory that we are going to discuss because it is built on top of this causal attention, but just in a different way, in not in a different way, in the same way, but multiple times. So let's see how this can be done. The next video would then look at how to make it more computationally efficient. So right now we are going to stack. What we are going to do is to stack multiple multiple single head attention layers. So when we create these multiple instances of the same self-attention mechanism, each one will have its own weights, and then we'll combine their outputs. What we mean is something like this. So let me write the flow here like we've been doing. So we are going to have our inputs, which is our x here, and our x is going to have the embeddings for the tokens, right? And if you remember, the fifth one was 0.7, 0.2, and 0.1, like that. So we will take this, and then what we are going to do is we are going to have our weight matrix, a weight matrix here that is going to be initialized, and this is going to be our WQ. But because we are copying the weight matrices and everything, this will be the first WQ. We'll have a first WQ, and behind that, we are going to have another weight matrix. That is going to be the second weight matrix. The same thing, we are going to do the same thing to, we're going to create another weight matrix, and that is for our keys. And this one will be the key weight matrix number 1, and we're going to have a key matrix number 2. Again, same thing. We'll have weight matrix, which is our WV, but this is going to be the first one, and we'll have another second one. We have a second one, WV2, and so on and so forth. So these inputs are going to be operated on by the WQ1, also operated by WQ2. And what that results in are the queries, right? When we apply WQ to the inputs, we always get the queries matrix. So here we're going to have the Q1, queries matrix 1, and we are also going to have queries matrix 2. Going to have queries matrix 2 when we apply the WQ2 on that input. The same thing happens with the values. We are going to have the keys. These are the keys. We're going to have the keys matrix K, but this is going to be K1, and we're also going to have K2, like that. Same thing with the values. So here we have the values matrix, and this will be V1 coming from applying WV1 to the inputs. And then when we apply WV2 to those very same inputs, we'll have a values matrix V2, as we have seen. And then these matrices, because when we apply the queries to the keys, we get our attention scores, right? Our attention scores and then our attention matrix. I'll just keep a few stages there of like normalization and all of that. But we are going to have attention matrix, going to have our, we're going to have this attention matrix and another attention matrix as well. And these are going to be our masked attention matrices with dropout. And we are going to have masked attention matrix number 1, masked attention number 2, because we are applying Q1 to K1 and then Q2 to K2. So two operations there. And then these are then going to, we are going to then get our value matrices, and we are going to create context vectors. So here we're going to create context vectors Z1, context vector Z1, and we'll create also context vectors Z2 when we apply the second masked attention matrix to values 2 to V2. Then at the end, we are going to get a combined context vector matrix. And this will be now our Z. And our Z will be a combination of all the Zs that we have here. And we just concatenate. That's all we do. So this Z, and then next to this Z, we add Z2, Z3, Z4 to create this overall Z here. So the idea is to run these attention mechanisms multiple times in parallel with different length linear projection. So we are using those queries key vectors like we are showing here. We are showing here, applying them to the attention to the input, applying them to the input, and then creating this KQV and all of that. So let's see what we are going to do. In our code, we are going to use two we're going to use two number of heads, just like you have shown here. We use 2, and then we will apply that to our cursor. So let's actually go to the code and see what we mean there. So let's switch to Chrome. Okay. So we are extending now to multi-head attention, and we are taking the multiple single head attention layers, and we are creating this wrapper, multi-head attention wrapper, because it's just going to extend on top of our causal attention that we had. So as you can see, we have our D out, D in like we needed for our causal attention. And in this line, we are creating our heads. We are creating our heads in this line like so. So building on top of our causal attention, and we are saying 4 in range number of heads. So we would have created causal attentions that we are taking in a list based on the number of heads that we would have decided. That's all we're doing in that part, in this line there. So if we have 2 number of heads, that's what we shown when we're writing it out. So now we have our heads. Those are our heads, and it's just a module list. In our forward now, we're just going to say you are going to concatenate the results that are coming from our causal attentions, because the causal attention will get us results like this for each one of them. And then here we just concatenate the results that are coming out. That's it. So for head in self heads, that's what we have. So let's actually see it happen. Here we just create our object here. We are going to use our D in 3 and our D out 2 like we have been doing. And our context length, the same thing. All that we've been doing, I think in our case would be, I think it was 6 tokens. Number of heads, we're going to use 2 as the number of heads. And then we calculate our context vectors. So as you can see now, we have this concatenated onto the second one. like we have shown on in smooth draw. So now these are our context vectors concatenated for each batch. This is the first batch, and this is the second batch for each head. So this is coming from the first head for the first input, and this is coming from the second head for the first input, and we concatenate them to be the context vector for the first input. And this is the context vector for the second input in the batch number one, batch number two, batch number three, batch number four. No. In the first batch, but input number one, two, three, four, five, six. And then we have another batch also doing the same thing. This is coming from the first head. This is coming from the second head for that first input in that batch. And that's the same. That's all we are doing because we have two batches that have 6 input each, with a which is now our D out. Our D out, if we're not doing this stacking of batches, it was going to be 2. Like we had when we had a single head. A single head was having D out equal to 2 here. But then now, because we are concatenating the number of heads, we are repeating the same thing two times, so twice. So we concatenate. That's why we have a D out equal to 4 now. It's equal to 4 because we have 4 heads. If we had 3 heads, this was going to be 6 because we would have done 2 heads. We would have done 3 heads. If we had 3 heads, we would have done 3 heads. Each head returning 2, so 6. So batch, and then number of tokens in each input, and that. That's what we have right now. But the problem with this way that we've done, it is good for learning, but the problem, some people would have seen it already. It is this line here. This is not doing it. This is not computing in parallel, but sequentially. It is computing not in parallel but sequentially. So we are stacking. We first do for head number one, and then we store it on the side, and then we do for head number two, and then we then concatenate it to that, and then we calculate for head number three, and then we concatenate. So there's no parallelization here, which makes it difficult because some of these models, they have multiple heads. They can have 24 heads. So imagine if they have 24 heads, and then the dimensions you're dealing with is 12,000 dimensions, which means your KQV are very big matrices and all of that. It's going to be extremely inefficient for us to do it in a for loop like this when we are not doing parallelization. And now that is the topic for the next video. How do we actually parallelize this? Because if we do them in parallel, then the computation can be much more efficient. But the principle is the same. So stay tuned for that video.